Hi, I want to work an example of using the equations of kinematics with some real-world data. So the Porsche Panamera Turbo is said to be able to go from 0 to 60 miles per hour in a time of 3.6 seconds. Well, what else can we learn about that information? Well, whenever we're sorting out working with problems, the way that I always like to sort of show my students how to brainstorm is by playing a game of Foursquare, where we have 4 boxes: known information, unknown information, any concepts that we have to deal with, and then any equations that relate to the scenario at hand. And there's no one order that we need to go through in doing this brainstorming. It can happen just like a game of Foursquare, bouncing around from box to box in an organic manner. Now, I've written most of this problem out before I started filming, so what I'm going to do is, since I sort of introduced this problem as just I just watched a car commercial, what does that mean? Well, let's think about concepts, because when we talk about motion, the most important problem in kinematics that we're going to take a look at is motion with constant acceleration. And the mnemonic that I like to use when you're dealing with motion with a constant acceleration is 5/3. 5 because there are 5 possible pieces to the kinematic equations. 5 possible variables that we can deal with. Our displacement, delta x, or delta y, if we're looking in the vertical direction, our initial velocity, our final velocity, our acceleration, and our change in time. The 3 of 5/3 means that once you identify 3 of those variables, then you can solve for the other 2. Because with any of the kinematic equations, at most, with constant acceleration, you would end up having 3 pieces of information in that equation that you need to find, because you're always going to have 4 possible variables in that equation. And you can have 1 unknown per equation. So what that means then is when you have 2 unknowns, 1 unknown is going to be what you're solving for. The other unknown can be used to tell you what family of equations you want to work with. So here, 0 is our initial velocity, and 0 is 0 in every unit, because stopped is stopped. Motion is an absolute type of quantity. Now our final velocity is 60 miles per hour. And in physics class, we usually tend to work in meters per second. So we're going to want to probably convert that at some point. And it's always a good idea, before we start doing other math, once we know what we're looking for, to make sure that if we need to convert units, we convert units. And we're given information about the time that it takes that motion to happen. Going from 0 to 60 miles per hour, it takes 3.6 seconds. So that means that our acceleration and our change in position are our 2 unknowns. And it doesn't matter which one we solve for first. We could solve for acceleration first. We could solve for displacement first. And I'm going to solve for the displacement first. So to do that, I'm going to pretend that I don't need to know the acceleration. It's not a pretend, because I don't need to know the acceleration. But I am going to find that acceleration later. So if I go to the families of ways of writing the equation of motion for constant acceleration, one of the ways that we can write it with no acceleration is to say that our displacement is our average velocity, which is just v initial plus v final divided by 2, times our change in time. Well, v initial, we have, it's 0. V final, we can convert to meters per second. And then we have our time in seconds. That'll allow us to calculate how far the car travels going from 0 to 60 miles per hour, at least in meters. So the conversion for meters per second and miles per hour every 1 mile per hour is 0.447 meters per second. So to convert units, we start with miles per hour. We want to replace it with meters per second. So I have my big fraction. Next to meters per second, I have a 0.447. I'm dividing by miles per hour to cancel miles per hour. In my conversion, I have one of those. So my units cancel. And 60 times 0.447 tells me that I have 26.8 meters per second, which is 60 miles per hour. So I can fill in what I know in my acceleration, or not acceleration equation, my displacement equation. My displacement is 0 plus 26.8 meters per second. Divide that by 2. That gives me an average velocity of 13.4 meters per second, multiplied by our 3.6 second time, and that gives me a total distance of 48.2 meters, which is 158 feet. And since all of these data points were initially given us to 2 significant digits, we'd probably round this to 48 meters if we were looking in meters, and 160 feet if we were looking in feet. Now, for calculating the acceleration, we could now use 48.2 meters as our displacement and use any of the other equations that don't show up in the no acceleration family to solve for acceleration. Or we could do things directly. We could say, well, I don't need to know that the car traveled 48 meters. Let's use the starting information. And from the definition of acceleration, acceleration is my change in velocity, v final minus v initial, divided by my change in time. So, v final, we said, was 26.8 meters per second. We divide that by 3.6 seconds, and that gives me 7.44444. So to 2 significant digits, 7.4 meters per second squared. And comparing that to the free fall acceleration, g, that's 76% of the free fall acceleration. So the neat thing is, if you want to reverse that, you could look up that data, and it turns out that it takes 28.6 meters for this car to go from 60 miles per hour to a stop, which means that on braking, you'd have a negative acceleration of 12.6 meters per second squared, which in terms of the size of the free fall acceleration would be minus 1.3 times the free fall acceleration. The tires can stop the car faster, changing the motion faster than gravity would be able to change the motion of the car. Thanks for watching.